So this morning I wanted to talk about different kinds of supernova engines, and what really fueled the additional engines for supernova was the discovery of gamma ray bursts. And so I'm going to give a little bit of review on how these gamma ray burst discoveries got tied to massive star collapse and what kind of engines that then made for supernova. You know, I think I might as well start with the beginning. So I was thinking Alicia would have covered some of this. Because she's not, we'll go through some of it with me. If she covers gamma ray bursts more, she'll definitely get into more details. So discovery of gamma ray bursts was done by some satellites designed actually at Los Alamos to make sure to monitor the Russians and make sure that they were following the test ban treaty. So the U.S. had made a treaty with the Russians to say we're not going to do any more testing of above ground testing of nuclear weapons. The way to check is if you do shoot off a nuclear weapon, you're going to produce gamma rays. So the U.S. decided they're going to send up some satellites to probe those, look for gamma rays anywhere on the world to see if the Russians are actually testing. A story on that, well, okay, so they put up these Vela satellites. They started searching for gamma rays. And in 1967, they saw a burst of gamma rays, and they didn't know what to do with it. They were clear very quickly that it was not the Russians testing. So then they didn't know what it was, and there's been lots of rumors where it was all hush-hush. They couldn't present the results. I've talked to Ray Clevesettle, and he commented that he just didn't know how to write a science paper. He was an engineer working in the nuclear weapons program, doing test ban treaty stuff. He suddenly got a signal that was not what his job was. He didn't know how to write an astrophysics paper, so it took him 5 years to actually get the paper out, and a lot of help. Interestingly enough, Sterling Colgate was actually part of that test ban treaty. The treaty was actually done in Switzerland. Part of that test ban treaty. And the Russians had already said, but Sterling, you'll get gamma rays from outer space. And Sterling's like, what are you talking about? Yeah, you could get them from supernova. You could get gamma rays from supernova. This had Sterling working on astrophysical sources for gamma ray bursts before they actually even launched the Vela satellites. So Sterling was already thinking about it, and hence Sterling had a paper out on the first gamma ray burst models even before the publication. He knew about the discovery. So 1967, Ray Clevesettle came to him and said, what is this? And Sterling goes, I know what it is, and started writing the theory paper. Sterling was faster and got the theory paper out in 1969, but the actual detection publication didn't come out until 1972. Maybe Sterling's paper was 1970, but it was in that early, before the publication of the actual results. The discovery of gamma bursts actually started the golden era for theorists. When you have very little data, that's the perfect time for theorists. So a lot of models came out. This is the first, there was a list of different models in the done where they went from, I think it was up through the 1990s, all the models that had been proposed. This is the first page of that list. It was actually several pages long, with different papers, different models for gamma ray bursts. They kind of were into three classes. Either they were solar system type bursts or even in the atmosphere. So it's things like ball lightning in the atmosphere, some kind of magnetic storm in the atmosphere of the Earth. There were galactic models, and almost anybody sane was pushing for that because at the time, the cosmological models seemed immense. 10 to the 53 ergs of energy. How are you going to get that kind of energy? And then the galactic, so there was a lot of people doing galactic models, and then there were cosmological models. The physics ranged from, cosmic strings doing some kind of annihilation to things falling onto compact objects. There was a big push for asteroids hitting neutron stars as a way of making gamma ray bursts. So the theorists between these three classes had started, they actually had a great debate. Martin Rees moderated it. Bohdan Paczynski pushed for cosmological models. Don Lamb pushed for the galactic models. And they had arguments on, what really is the right engine for these. The different models really weren't, especially in the 70s, you really couldn't push one way or the other. In fact, in the 70s, I would argue that the cosmological models were in disfavor, just because it seemed like so much energy, and Bohdan was really pushing it even with the energetics. The only way to actually solve and actually have theorists move beyond this was to actually get more data, and one of the pieces of data that really kind of turned the tide on which class of models was the correct class of models was the BHAD satellite, the burst and transient spectrometer experiment. It had 8 detectors that had almost full sky coverage. With that, they could look at all the gamma ray bursts coming from almost all directions. It had 2 sodium titanium scintillation detectors. They were large area detectors, so they had sensitivity. And there was also a spectroscopy detector for energy coverage. So, it covered from 20 to 600 keV. They could get these gamma rays and actually get some information on the data. The first bit of data that really started changing the models was the distribution of the gamma ray bursts. They looked like they were in all of the sky. So it was really hard to explain something that should be in the galactic disk, if it's galactic, being in all parts of the sky. That did not stop Don Lamb. He actually argued that gamma ray bursts were produced by neutron stars that were kicked into the halo of the galaxy. So the way of surviving and still having galactic models was to say that they were being kicked into the halo of the galaxy. But even with that, kind of way to get around this isotropy in the distribution of gamma ray bursts, people had stopped believing in the galactic models. It's even with his kick model, the distribution should have been at least somewhat located toward the galactic disk. What really, and Betsy also provided some information on the gamma ray bursts, what their features are, and one of the biggest pieces of information that has been clues for the gamma ray burst community has been they have the duration of the burst versus the hardness ratio. So what they did is they took the emission between 100 to 300 keV, divided by the emission from 50 to 100 keV, defined a hardness ratio, and then they also plotted it versus, they defined what a duration was, so something where they said when the emission is within 90% of peak, or whatever definition you want to use. Different observers use different definitions, and they plotted this hardness ratio versus duration, and there became 2 populations. There were the long soft bursts and the short hard bursts. So these bursts are higher energy, have higher energy photons, but they're shorter duration less than about a second or 2, and then the long bursts that are durations more than a second or 2, going up to 100,000, and we even have 10,000 second gamma ray bursts now. This was led by Chryssa Kovalietu, and this is a paper that kind of defined how we picture gamma ray bursts. It wasn't, at some point, modelers realized they really need 2 classes of gamma ray bursts at this point. And there are, I will say, and I'm not going to talk about it any further, there are people that have 3rd and 4th types of gamma ray bursts. There's some ultra long ones now that are up at 10,000 seconds that are another class unto themselves as well. In most cases, we just think they're different progenitors. So the BHAD summary is GRBs are isotropic. This was the turning point for people believing that gamma ray bursts were galactic versus gamma ray bursts being cosmological. After this result, most scientists pushed over to cosmological models. This is about where I came into the field. So I only worked on cosmological models, although I like to at least cover Don Lamb's back when he was getting attacked by everybody for still pushing galactic models. GRBs come in all shapes and sizes. I did not show a lot of the different spectra, but the time-dependent emission of gamma ray bursts come in a lot of different shapes, but the two classes are short hard bursts and long soft bursts. At the same time, people were working with models on cosmological engines. One of the ones that is relevant to us from stellar collapse was the collapse arm model. The idea was it was a collapse of a massive rotating star. It would form a black hole. That black hole, you then accrete more and more material onto that black hole. If the star was rotating, it would form a disk around that black hole and make something looking like an AGN, but much higher densities, much higher accretion rates. By just scaling up what we know about AGN, we could say, oh, we're going to get very strong bursts. It's going to make a nice jet of material. That jet of material is going to drive gamma ray bursts. And this is the start of the kind of black hole accretion disk engine scenario for gamma ray bursts. And this became a population of different progenitors for black hole accretion disk systems. This is a slide actually done by Max Ruffert, but he attributed Stan Woosley to it. This is the class of models that we had come up with, where the collapse arm model is the collapse of a rotating massive star. This is kind of the topic of this school. But there were a set of other systems that could make hyper-accreting accretion disks. So we wanted the accretion rate to be above about a hundredth or a tenth of a solar mass per second. So you're accreting at huge rates onto a black hole. There's a couple ways to do it. One way is to take a neutron star or a black hole and have it in that common envelope scenario we were talking about yesterday, have it actually spiral into the core of that massive star. So as it spirals in, it actually spins up that massive star. Now I have a compact object at the center of a helium core, and that helium core is going to accrete onto it, and it's going to make a gamma ray burst. By the way, this was when I was talking about the T.H. White's mandate for everything that's not forbidden is mandatory. This was the model for these Thorne-Zickoff objects, where they thought the neutron star would spiral in and just accrete nice in a steady way for 1 million years. In fact, what happens is the neutron spirals in and it accretes like crazy for a few seconds, or 100 seconds, and it drives a gamma ray burst. So the model that used to be Thorne-Zickoff is now a model for gamma ray bursts, and it was called the helium merger scenario when it was first proposed. Other objects that can make these accretion disks, the merger of a black hole with a white dwarf. The white dwarf gets torn up fairly far out, so it actually makes a fairly high angular momentum disk. It accretes at a fairly low rate, so it actually takes 100 seconds for it to accrete. And then two models that look like they would accrete only for a fraction of a second. And that's neutron star mergers and black hole neutron star mergers. So at that time, theorists said, okay, well, these accrete only a short amount of time. They look like they're accreting at a really high rate because they accrete for, say, a tenth of a second. They accrete a solar mass. So they're accreting at 10 solar masses per second. This is a really high rate. These objects will be what they call short bursts because they're accreting at a high rate. They're going to be hotter. They're going to be harder than in their spectrum. So the idea was these would be harder and shorter bursts. These would be longer, softer bursts. So at this time in the late 1990s, theorists called these the short hard bursts and these the long soft bursts. So at some point, I'm going to focus more on these long soft burst scenarios. In fact, these two look so similar that at some point we merged them as progenitors because they're both massive stars with something in the center that's driving an engine. And they'll both produce supernova-like objects. These won't produce things that look like supernova only because they don't have that material on top. So they'll look slightly different than supernova. Although to a observer, I'm not quite sure if you can tell. You know, a kilonova looks different, but it still has a classic light curve. So at around 1999, well, actually starting in about 1997, Andrew McFadden was working on his thesis. Stan had put him on driving jets through massive stars to see what kind of explosions he could produce. And he got the paper out in 1999, where it was the first simulations of a jet going out of a star for this collapsar model. So this was the work that Andrew McFadden was doing. The argument for this picture was that he could produce a gamma ray burst jet, but he'd also disrupt the entire star, so he would get something, the star would also get destroyed at the same time and produce something that looks like a supernova. At the same time, Beppo-SAX had been launched. Its goal was to get positional accuracy of these gamma ray bursts to within 5 arc minutes. It was an Italian-Dutch satellite. The launch was in 1996. They started discovering optical counterparts of bursts. So in 1997, they saw their first optical counterpart. And it allowed them to start getting really accurate positions of gamma ray bursts. In 1997, they got the redshift of this burst, so that once you get the optical, you can measure absorption lines. If it's in the host galaxy, so here's the burst going off, it's in some host galaxy, you can measure the absorption lines from that host galaxy and then use those lines to get the redshift of the burst. This made it without any doubt that these things are cosmological. So if people hadn't already jumped on the bandwagon by then, everyone realized that these are cosmological bursts. We've gone through now quite a few bursts. So this one had a redshift of 0.835. Now we have hundreds of redshifts. We know where these things are distributed throughout the universe, and we know they have to be energetic. The nice feature of the collapsar model was it said it was a jet. So the energetics wasn't as extreme as we thought. We didn't need 10 to the 53, 10 to the 54 ergs. We can get away with the bursts that only had 10 to the 52 ergs of energy. It's just the 10 to the 53, 10 to the 54 ergs was inferred if you assumed the explosion was isotropic. And in this case, in the jet scenario, you can say, no, it's all in one angle. So depending on the opening angle of the jet, I need that much less energy. And that got us down to about 10 to the 52 ergs. In 1998, there was a supernova there was a gamma ray burst that was observed, localized, and as the afterglow fell off, there was a bump that showed something that looked like a supernova associated with it. So this came out in 1998. Honest to God, Andrew McFadden was already done with his simulations by this time. He was already working on the paper. He knew that there should be a supernova associated with it. However, he was a grad student and still learning how to write papers, so he did not get it out before this observation. But in 1998, an observation of a gamma ray burst with a supernova associated with it was observed. This really did drive home the idea that something like the collapsar model was the right model for these long duration bursts. And at this point in time, most people decided that this was the standard model for gamma ray bursts. So the idea is that you have, the idea that we had come up with is supernovae are produced by these low mass stars. They explode through this neutrino mechanism. Then there are a class of stars that just don't explode at all. They become a black hole. If they're rotating, they'll drive jets and they'll produce a gamma ray burst and a strong supernova-like explosion. Now, the interesting features of these supernova is to explain the peak. It's so bright that either you have really strong shocks or you produce a lot of nickel in these explosions. So they're clearly different than a normal supernova. And this comes back to that figure that Ken Nomoto had, where here's our normal supernova, and then there's this class of these just really energetic explosions. Typically, if you use the peak to get the nickel mass, high nickel mass ejecta, so there's now a whole set of these. This is in 2003. We already had over 4 or 5 of these kind of strong collapsar-like explosions. Because the collapsar is just a model, we term the observations hypernova. So these are hypernova. There's evidence in all these hypernova of strong high velocities in the supernova. There's also evidence of extra kinetic energy. So there's asymmetries and high velocities in these particular set of supernova. So if they are not the collapsar engine, they are some other jet-like engine that's producing these explosions. Just as an aside, for the neutron-star mergers, Josh Bloom and myself looked at the distribution of these bursts. How should they be in the next to their host galaxy if you were producing them out of neutron-star mergers? The feature of neutron-star mergers and neutron-star black hole mergers is when they form, they receive a kick. Neutron stars are born usually with some kick associated with them. Neutron star binaries have that kick associated with them as well. A little bit lower velocity, maybe a Maxwellian velocity with a mean of around 180 kilometers per second instead of the 450 kilometers per second for a neutron star. But that velocity kicks them off into different directions, pushing them away from the host galaxy. So you expect the short bursts to actually be distributed further from the host galaxy than the long duration gamma ray bursts. So long duration gamma ray bursts you expect to be not offset from the galaxy, actually in the star forming regions. And we see that in long duration bursts. That's this line here. This is a distribution, the offset of the gamma ray burst from the host galaxy, and this is the cumulative fraction. So if it's really peaked right toward in that host galaxy, it would go up high and then stay, go up to 1, and you'd get the 100% really closely peaked toward that in that center of that host galaxy. For long duration bursts, it is peaked. It's within, all of the bursts happen within 10 kiloparsecs of the center of the host galaxy, which means they're all happening in the galaxy. With the short bursts, they're much more distributed. So this was done by Fong and Berger in 2013. These models here were different population synthesis predictions for neutron star mergers done starting in 1999. Myself, Josh Bloom, and then there's actually 3 curves here. I can't see the third one, but one of them is done by Chris Belczynski in 2003. So all the population synthesis models were arguing if there's short bursts, if neutron star mergers are short bursts, the short bursts should be more widely distributed, and they are. There's almost no other way to get that big offset without having something that is kicked pretty hard. So if you need something that requires a compact object and you need it to be kicked hard, there's not that many models left. So at this point, the short bursts really are considered to be neutron star mergers or neutron star black hole mergers, and there's not much doubt about that. If you have a different progenitor you want to try on me, feel free, and we'll see what we can, we see if we can match those. This is a field into itself. I'm not going to go into it anymore except for one more slide, which is if we can observe these bursts and we know the masses of their mergers, we can actually probe the equation of state. So we look at the mergers and we ask the question, do they merge and they form a black hole, or do they form a neutron star? Whether they form a black hole or a neutron star depends on what your maximum mass for a neutron star is. That's an answer that the equation of state experts know. The nuclear physicists that study material at dense matter conditions can tell you, I think the maximum mass of a neutron star is going to be, right now, most of their models say around 2.1. And that's because the most massive neutron star we've observed is around 2.0. But they've actually claimed to me that going above a maximum non-rotating neutron star mass of around 2.3 or 2.4 is very hard to do. The interesting feature is, this is a plot of the fraction of systems we expect that are neutron stars or black holes, depending on the maximum non-rotating mass of an equation of state. And the issue is, so here's how many, the dotted line would be how many systems should be, after the merger, should be neutron stars after the merger. And if the maximum neutron star mass is only 2.2, it should be that all of the neutron star mergers, nearly all of them, become black holes immediately. If the maximum mass is 2.5, all of them will be neutron stars. So if we can see these objects and tell post-merger whether they're neutron stars or black holes, one way to do that is there a magnetar in the center or not? We can actually probe what's the maximum mass of a neutron star, which tells us a lot about the equation of state for nuclear matter. So this is one of the big topics right now. There's lots of meetings on this discussion. There'll be a 4-week workshop in Seattle, the Institute for Nuclear Theory, just on this topic of how can we probe the equation of state for dense nuclear matter from neutron star mergers. So this is a topic that these neutron star mergers have really played a role in these short bursts and also studying nuclear physics. So we have this. I've already talked about the 2 different ways astronomers use scientific axioms to decide whether a model is good or not. There's Occam's razor, where you try to kill off models. There is T.H. White's mandate, which allows you to build any model you want. Clearly, we use T.H. White's mandate because otherwise I couldn't have shown you at the beginning of this lecture this list of models, right? People were just going through anything they can get that seemed plausible, they were proposing. So that was T.H. White's mandate. What happened was, once we got all these observations that we went over, people said, oh, well, collapsars seem to explain things. These black hole accretion disk systems seem to explain things. These must be the models. And so we had a period of time where Occam's razor had really silenced a lot of the other models, and people were focusing just on black hole accretion disk models. The problem with this is there are other ways to make jets out of collapsing stars, and that's one of the big issues that we need to make sure that we are still following White's mandate with some regulation. We don't want to throw out all the models. We want to consider what else we have. So there are some lessons if you're going to believe in some model. I think we know from Supernova that more than one model will work. Otherwise, you wouldn't have both Fritz and me talking in this school. But if you have to push some physics to the extreme, it's probably not going to work. If I have to assume everything is working at its best level, if I have to assume 100% efficiency in making a supernova engine, that's probably not going to work. So if we, with the core collapse supernova engine, we had 10 to the 53 ergs, we're struggling to get 1% efficiency. So you need to really think about what, if you have an engine and if you require all of your energy going into magnetic fields and then taking whatever energy is left and making 100% of it going into a jet, you're going to start struggling to make your engine work. So we need to, and then the other thing we need to do is understand the progenitor after we've done it. So clearly with these engines for gamma ray bursts, we had an idea of a black hole with an accretion disk. It's going to generate a magnetic field, but really understanding how the progenitor produces it is something that people have spent a lot of time on. So there's a lot of GRB engines out there. The black hole accretion disk idea came from Bodan, actually, Paczynski and Narayan in 1992. Stan's contribution was coming up of the disk is made from a collapse of a massive star. There's also things like magnetars that can produce gamma ray bursts, and in fact we do believe they produce these soft gamma ray repeaters. Raymond Ruffini has been pushing this diadosphere method where he's collapsing, producing a plasma above the black hole that actually generates, when it releases its energy, produces a strong explosion. All of these can work at some level to explain gamma ray bursts, but it's actually difficult to. Some of them require more fine-tuning than others to make them work. There's a lot of other engines that have been proposed. You could argue that you can, and I'll talk about this in more detail, you can collapse down to a neutron star and form an accretion disk around the neutron star, generate strong magnetic fields and make an explosion like that as well. So there's a lot of models doing with various scenarios around this, a white dwarf collapsing down to a neutron star with an accretion disk. All of these exist. There's a lot of models out there. One of the things that's important is make sure whatever model you have a high enough rate. I'll use Remo Ruffini's model as an example. He believes that he can make gamma ray bursts from a neutron star. He has a scenario where he has a massive star and a neutron star. The massive star explodes. Some of the material from that massive star accretes onto the neutron star, causing it to collapse to a black hole, and then making a gamma ray burst. That's a fine idea. The physics is there. You can get the accretion rates for some systems. You can actually get something that will collapse down to a black hole. The problem with that particular scenario is it cannot explain all gamma ray bursts because the rate of those systems is just too low. So you can get a scenario where you can explain the physics all seems to work, but if your rate is too low, it's not the dominant mechanism. The other thing is to make sure you look at your energy source. Again, I pointed this out for supernova. We release 10 to the 53 ergs. We struggle to get to 10 to the 51 ergs. There are models out there for gamma ray bursts where they're assuming 100% efficiency, and then they say I can get enough explosion energy. If your model really requires 100% efficiency, nature is usually not that efficient, so it's not going to work. So energetics, you have to think about how you're going to come up with a model. I can rule out almost 90% of the models that people are pushing right now, either by the rate is not high enough or they're assuming an energy that is 100% efficient. So that's my lessons. Don't assume the 100% efficiency. If your rate is not high enough, you're not going to make it. So GRBs are rare. So they're only 10 to the minus 5, 10 to the minus 6 per year in a Milky Way galaxy. The energy is around 10 to 52 ergs once you assume beaming. So you almost need to have the beaming to make the energetics reasonable, and they're less than, except for these ultra-long bursts, less than about 100,000 seconds. The Lorentz factor of the jet needs to be around 100, depending on who you talk to. There are some, if you assume simple models, you would require some Lorentz factors to be higher. This almost always pushes you to scenarios where you have a neutron star or a black hole in the core driving the energy. This is why we have the kind of collapsar models. We have the double neutron star merger models. There are models where you have a neutron star collapse to a black hole. The problem, this is another example of a model where the energetics is just on the edge. If you assume a very fast rotating neutron star, it turns out that at that maximum mass, if I can push that maximum mass up to about 3 solar masses, the radius of the neutron star is not that much above the innermost stable circular orbit of that black hole once it collapses, which means I don't have much material above that innermost stable circular orbit, which means it's very hard to get any energy out. So I have less than about 0.05 solar masses that I could even hope to get energy out. So even if I was 100% efficient, I'm struggling to get the 10 to the 52 ergs. So this neutron star collapse to a black hole is often hard unless I have material accreting onto it. The magnetar engines can work. It's set by the rotational energy of a neutron star. Again, the maximum for a 1 millisecond neutron star is around 10 to 52 ergs. So you're really right on the boundary of can I make a magnetar make gamma ray bursts. What most people are pushing now for magnetars for gamma ray bursts is not for the burst itself, but for the late time emission. So can they explain flares or any activity after the initial burst? Again, because the energetics aren't high enough. So a lot of these models, they get pushed. People have proposed features of models. If they are struggling with the energy, in the end, they become just side parts to the main burst, which is an important thing to understand. So it could be that magnetars are still very important in these in these gamma ray bursts at later times being after the first few, in the case of neutron star mergers, after the first second. But they can't, it's hard to get enough energy to have them dominate unless you really are maximizing, getting 100% efficiency, which, if these guys did the calculations correctly, I think they'd find that they can't maximize that energy to 100% efficiency. So those are some of the models. The reason that people have used black hole accretion disks versus neutron star accretion disks is if you look at the rotation or the angular momentum in massive stars, and these are, let's look at the solid line first. The angular momentum of a massive star the specific angular momentum tends to go up as you go out. It has some structure depending on how your magnetic coupling works. Usually it's really low in the core of a star, moves up. At different shell boundary levels, there's a drop down. So these are models done by Alex Hager. So you can see the angular momentum's going up, drops back down, goes up, drops back down. But as I go out further in the star, I'm getting more specific angular momentum. That means that this material has enough angular momentum to make a disk, whereas this material here won't. So you need to, the advantage of saying I'm going to form a 3 solar mass black hole and then accrete from here, this is going to allow me to form a disk, whereas this material might not. There's a lot of models of this. What we had done to try to get more angular momentum in stars is cause 2 helium cores of massive stars to merge, making a fast rotating helium core, and then evolve it. And Alex and I had evolved some of these massive stars. But the weakness of a neutron star accretion disk model is that most material right above the neutron star in a star, so above that 1.4 solar masses in the interior of a star, doesn't have enough angular momentum to form a strong disk. And so it's hard to then generate magnetic fields with a disk that really isn't that centrifugally supported. And so the black hole accretion disk model came into favor because you could accrete the outer layers of the star where the angular momentum is higher, and you're more likely to make an accretion disk. For neutron star mergers, you don't have to worry about this. You have lots of angular momentum. You make a nice torus that will last at least for a few milliseconds. So the weakness over neutron star accretion disk versus a black hole accretion disk is exactly the fact that it has less angular momentum. So it requires more rapidly rotating progenitors to make a neutron star accretion disk, and we're struggling to even get the angular momentum for the black hole accretion disk models. So let's talk about that. This is all for how we were explaining gamma ray bursts, but now this comes back to what about supernova? We've proposed all these engines, things like magnetars, things like neutron star accretion disks. They don't really work that well for gamma ray bursts. They have weaknesses to them. But we do have some weird supernova, and if Felicia was here, she probably would have already covered these superluminous supernova that are more energetic than a normal supernova, but they are not, they have, or I should say, they have more emission than a normal supernova, implying that they're more energetic. Do they have a different mechanism? So can we take some of these failed gamma ray burst engines, like the neutron star accretion disks or magnetars, and have them work as weird supernova explanations, explain different weird supernova. And that's what people have been doing for a while. I'm showing a plot of the magnetic field generation by Akiyama et al. This is a former student of Craig Wheeler. They studied some fast rotating core collapse supernova, and they looked at the disks that formed. So they were studying neutron star accretion disks, and they said, how high of a magnetic field can I generate? And they were generating magnetic fields in excess of 10 to the 14 and 10 to the 15 Gauss. So those particular stars can produce strong jets and then drive a different kind of engine. This kind of scenario doesn't have to happen a lot, but it can explain things like superluminous supernova. And when I talk about nucleosynthesis, we'll talk about how people have used it to explain producing our process in the supernova. But it's a subclass of supernova, could be limited to superluminous supernova, could be limited to hypernova that aren't producing as strong a gamma ray bursts as we think they are, but maybe they're these X-ray flaring gamma ray bursts that are not quite gamma ray bursts, so they're classified as X-ray flares. So you have this category that can be used to explain other kinds of explosions, and people have certainly done models of these. I think magnetars are also used to explain the superluminous supernova, and there is some physics we have to study to prove that they can work, but they can also be used to explain these kind of ultra-energetic supernova. Now the problem with these magnetic mechanisms as being the all of normal supernova is they really aren't that good at explaining why they mostly produce one foe or a few foe explosions. They would argue just for a stream of supernova ranging from 10 to the 52 down to 10 to the 50 for a lot of the magnetic mechanisms. Whereas there's a bunch, the observations are there's a bunch of supernova at a few foe, and then there's these rare things like the superluminous supernova and the hypernova that are much more energetic. I think this is where these magnetic models fit better, simply because the rate should be lower than normal supernova. They should be explaining bizarre objects, and it seems like they fit the data, their models fit the data better. There are other ways to make superluminous supernova. There's shock interactions with the ISM, could actually produce the additional luminosity. This is something Roger Chevalier has proposed. I don't think these will work for all of the superluminous supernova. We talked about the magnetar some, and there's also fallback. If you have a lot of late time fallback, you can also produce an additional engine to drive superluminous supernova. So there's other models for these weird supernova, but magnetic field models could easily work for a lot of these engines. So in conclusions, the discovery of gamma ray bursts produced this bizarre class of supernova that almost certainly requires a different engine than what we produce in the standard supernova engine. This got people looking into ways of making strong magnetic fields. The black hole accretion disk systems were designed to optimize the angular momentum you can get in that disk and generate the strong magnetic fields. But a list of other engines have been proposed where you still have a neutron star at the center, magnetars and these neutron star accretion disks being the dominant ones. Both of these have some problem with their energetics to explain gamma ray bursts, but I think they are open for a lot of these bizarre supernovae that we see that are not explained by the standard supernova engine, and I think that's where most of these fit in. This is, by the way, a thing of great argument. So I'm giving you my opinion, and I'm setting it up here so you guys can argue with me on it. Noam Soker, for example, believes that all supernova are produced by some kind of magnetic field generated engine. It's hard to explain because and we'll be looking at data in the next couple of lectures where the jet engine just doesn't work. But there are people that believe everything is magnetic fields and everything is a jet. So I'm definitely giving you my opinion here. But the way the data is showing things like energetics, they can explain that most supernovae are at the 10 to the 51 ergs. They can't, and as we go through things like asymmetries, they don't match the asymmetries that we see in supernova when we can measure the asymmetries in detail. So these mechanisms don't seem to explain the data, and that's where Occam's razor comes in. And you say, look, this one matches the data better than this one, I'm ruling those out. They do have a set of weird supernova where these engines really can work, and that's, I think, something that is why they should still be studied and studied in great detail. The issue with a lot of these magnetic field engines is that the simulations for these engines are at a much lower level than the rest of the engines we study. It's really hard to do MHD calculations. they are not that predictive at this moment, so it's hard to really tell what these engines can predict. And so that's an issue. And that's all I'm going to talk about today on the engines. For the next lecture, I want to focus on what we know about compact remnants and how they constrain the supernova engine. And I'll end there.
Questions? Yes.
In the beginning, you talked about the distribution of the neutron star mergers being more distributed than the hypernovae. So the kicks come from the original supernova explosions that produced the neutron stars?
So when you form the first neutron star, it gives a small kick to the system. When the second one does, now I don't have much mass in the system at all. And you usually can get kicks up to 100, 200 kilometers per second in these neutron star mergers. So they're going to be going up and down like this in the galaxy. Actually, this is how I thought you might get our process from these spread out upon the galaxy. If they're merging above the disk, you can distribute it. I did a little calculation on that at one point. But that's so they're usually getting these kicks from the formation. And you get that, I mean, these models, what they did is they just took what are the neutron star kick distribution, and when they did their population synthesis models, they included that effect. So that's what these curves, that's what their distribution is based on. So they just put them in they put them in the star forming region, gave them the kick, and let them move around.
But that would also mean that the R process injected into material which is not consistent with the original supernova explosion. Okay.
Yeah. So so we should talk about that, because what does that mean? Because that is definitely the prediction from these neutron star mergers.
But which kick for this calculation, what was the velocity?
For the neutron stars? So when the neutron star forms, these different efforts use different kick distributions. For mine, I used a bimodal kick distribution for neutron stars based on the stuff that Arzumanian had gotten from looking at the pulsar velocity distribution. So it was a low peak and a high peak. Chris Belchinski's curve, which is, I just can't see it, it's too dim, was using just a single Maxwellian of a lower velocity for all of them. So they're all getting roughly the same answer. They all lie in here somewhere. They may be lying on top of each other on some parts, but they're all in that region, just using some form of kick distribution based on the pulsar velocity distribution and the latest results from that.
This is kind of a naive question, but where did the gamma rays come from?
For gamma ray bursts? Yeah. So you have a jet. Okay, and this is a very nice question, because when I was, for the longest time, it was all just, you have a shock in the jet, you have shocks in the jet. So the model that's the standard one now is I have a jet moving out, there are internal shocks in the jet, particles are getting accelerated in those internal shocks. They're emitting, medium energy gamma rays and then getting Lorentz factor boosted up into the gamma rays. So they're emitting X-rays or medium energy gamma rays synchrotron emission and then getting Lorentz boosted up to the gamma rays. That is the standard model. There was a big push at some point that this could be just thermal X-rays being Lorentz boosted up. And for a period of 10 years, it was considered, no, that has to be completely wrong. But the last couple of years, people have been saying, or at least a portion of the gamma rays that we see are actually thermal emission, just hot X-rays, then getting Lorentz boosted up into the gamma rays. So that's another way you can do it. You can also have the shock, the forward shock going through the interstellar medium can produce shocks that produces synchrotron emission, and you can get gamma rays from that part too. There are reasons why people don't like that, but it probably explains some of the emission as well. So there's now lots of places you can make these gamma rays, but the standard is internal shocks within the relativistic jet that you have from these explosions.
Last question. Or if not, the floor is yours.